Let's look a little more carefully at the relationship between position versus time graphs and velocity versus time graphs. So here I have a position versus time graph. Now, if you look at kind of this interval from t equals 0 to t equals 8 seconds, along this time here, that's uniform motion because I have a nice straight line. So that means a nice constant velocity. Here the velocity changes, but I can kind of just look from 8 seconds to 10 seconds and say during that time I have a nice constant velocity. So I have a little period of uniform motion here. And then from 10 to 12 seconds I have a little bit of uniform motion here with a nice constant velocity. I can see that because of the straight line. So remember that before we said that the average velocity is just the slope of our position versus time graph. So what we can do is figure out the slope of this part of the line, and whatever this slope is here, that is the velocity of the object from t equals 0 to t equals 8 seconds. So really all we need to do here is calculate the slope. And I'm not going to go into tons of math reminding you how to calculate slope. If that's something you need to review, please do it from a math textbook, okay? But you know, when calculating slope, you just pick 2 points on that line. They can be any 2 points. They don't have to be the first and the last point. They can be any 2 points. Plug one of them in as like the 1 point here for the position and time and the other point here for the position and time, and that's how you're going to get your slope. So I could pick the point x equals 2 at t equals 8, so I put a 2 here and 8 here, and then x equals negative 2 at t equals 0, so this would be negative 2 and that would be 0. And that velocity would be equal to 0.5 meters per second. So now we can also start to see where we get the units of meters per second. How are my meters changing each second? Meters per second. So that's our unit for velocity. So we have 0.5 meters per second all the way up until t equals 8 seconds because that's the slope here. What's the slope here? That's easy to calculate. It's just 0. Since the slope is 0, that means the velocity is 0. That means it's not moving, right? This looks like something that's not moving. It stays at x equals 2 meters this whole time. And then I can calculate the slope here, and I get negative 1 for my slope here. So I've figured out what my velocity graph looks like based on the slope of my position versus time graph. And again, for uniform motion, our velocity is given by the slope of the lines from the position versus time graph. So here's an example. Why don't you try to draw me the velocity graph based on this position versus time graph. So press pause, and then when you're ready to see the answer, press play. Well, again, I'm just calculating slope. The slope here, I changed from 150 meters to 0 meters in 5 seconds, so that's a slope of negative 30 meters per second. And here I change from a position of 0 meters to a position of 100 meters, and that also takes 5 seconds. That gives me a slope of positive 20. So this whole time I have a nice constant slope of negative 30 meters per second, and this whole time I have a nice constant slope of 20 meters per second. Now, what if we're not dealing with uniform motion, right? This graph clearly has 2 periods of, this is uniform motion here because it's a nice straight line. This is uniform motion here because it's a nice straight line. What if we had a graph that looked like this? Okay, this is my position graph. Here I used S. Sometimes I'm going to say S. Don't let that scare you. The S just means it could be X or it could be Y, right? S is just a way to say it could be X or Y. It just means position in general. If that scares you or bothers you, just write it as X. This is saying position and it's measured in meters. This is time and it's measured in seconds. Here is my position graph. It is not a straight line. So what do we do with this? Well, I can pick any two points, and the line that connects them, the slope between that line, gives me the average velocity between this point in time and this point in time. And if I make my points in time closer and closer and closer together, eventually what I'm going to be doing is taking the slope of the line tangent to that curve, and that is the instantaneous velocity. It's the velocity right at that moment, is the slope of the line that's tangent to that curve right at that point in time. So what we did was we took the limit. Don't let this freak you out. It's just a reminder of calculus. We took the limit of our definition and we were looking at smaller and smaller increments as delta t, that time interval, approached 0. It got smaller and smaller and smaller and smaller and smaller. Basically, we just took the derivative. The derivative of the position function is the velocity. So if this middle part doesn't make sense to you and gives you heart palpitations, don't write it down. That's the calculus part. This is still kind of calculus, but it's more applicable to what we're doing. So what's the result of this? Velocity is the derivative of position. Now don't think that I'm going to give you a problem on the quiz that says, x is equal to 5t squared minus t, what is v? And all you have to do is take the derivative. That's what you do in a calculus class. In this class, we're just applying these concepts and these relationships. So mathematically, we can say velocity is the derivative of position. In terms of a graph, the velocity is the slope tangent to the position graph. So here is position of an elevator as a function of time. Y now is my position. I'm looking in the y direction. And what I want you to do is try to think about, where is the elevator not moving? Where is it moving the fastest? What's going on here? So I would say, oh, here we go. Where does the elevator have the lowest speed? Take a second to think about that. Well, the speed is going to be related to the velocity, which I can find by taking the slope of the line tangent to the curve. So right here, the line that's tangent to this part is just a flat line, which has a slope of 0. So that means right here the velocity is 0. It's also 0 here. So A and C have a lowest speed because the speed there is 0. Where does it have the highest speed? Well, that's kind of the only other choice we have. But if you look right here, the line tangent to the curve would be like this, and that's the biggest slope we ever get. Somewhere over here, the line tangent would be like this. That's a smaller slope than it is right here. So B is where it's going the fastest. Now, what if we want to, again, try to draw a velocity graph from the position graph? We're not going to do crazy calculus like you did in your calculus class, but I want to just get a rough idea of what the velocity might look like. So I'm just going to kind of look in this region right here, and I can say, well, what's happening here? Well, it has a negative slope, and that negative slope becomes something closer to a 0 slope. So when I draw my graph, I want it to start off with a negative velocity value, and I want it to approach a 0 velocity value. Okay, so I'm going to start with a negative velocity value and approach a 0 velocity value. What happens after that? My slope slowly starts to become more and more positive. And here I have the highest value of the slope. After this, the slope is still positive, but it's approaching 0, and I'm back to 0 here. So this is what my velocity graph would look like. Okay, now I'm not too worried about the particulars. Is this line curved or not? In a calculus class, that's much more important. You would probably be given this function and take the derivative and blah, blah, blah. Here, I just want a general idea of what does the velocity look like based on this position graph.